Hi, thank you very much. So we have just seen Avi, using all sorts of advanced machinery, and this talk will be more basic. So this is based on joint works with Hamid Janjo, who's a student of mine, Eric Miles, who was a student of mine, is now a postdoc at UCLA, and Ali Ben-Sasson, who's faculty at Technion. Okay, so the starting point of this work is the classical result that 3SAT is NP complete. Okay, so because I need to fix some notation for the rest of the talk, let me go through what this means. Okay, consider some computation which may be non-deterministic and which runs in time t. Okay, and here t can be polynomial in the input length, or it can be much bigger, like exponential. And the setting of exponential will be the one that's most relevant for our work. Okay. Then there exists an efficient reduction map R that takes any input to the computation and outputs a 3CNF, which is satisfiable if and only if the computation outputs 1 or accepts. All right? So there are many things which are interesting to optimize about such reductions. The first one that you may think about is the length of the formula phi. Okay, and there was a series of works decades ago that have shown that it's possible to achieve a phi of size quasi-linear in running time t, okay, which is the best possible up to these polylog factors. Okay, and the second thing is the complexity of the reduction map R. Okay. So it is well known that if you allow resources to be at least as big as the length of the formula, this computation is essentially trivial. Okay? It just amounts to projecting onto the clauses of the formula phi. And I'm not going to make this thing formal, because our focus is on a different setting where the where the resources of the map are much, much less than the length of the formula. Okay. Specifically, we seek what I'm going to call clause-explicit reductions R that have the following property. They take as input both the input x to the computation and an additional input I, which is an index to a clause of the formula. And they should output that clause efficiently just with respect to the length of the index I, which is logarithmic in the size of the formula. Okay? So to make this thing visual, here is how a possible output of the reduction would look like. Okay, it gets an input I and x, and it spits out a clause which is 3 variables, some of which may be negated. All right?
What's the x? I see that the I refers
yes.
to the clause.
X is the input to the computation. Let me go back one slide. So there's a machine M which runs in time t, and the machine R takes an input x to this machine, okay, and outputs a 3SAT. Okay, so here in this new framework, I have as input both x and I. Okay, however, in this talk, I'm going to ignore x. Okay, and I'm just going to focus on the computation as a function of I. Okay, so just what's the cost of outputting the clause. However, dealing with x is not easy and requires a separate argument. Okay? I'm not going to go through it. Okay? All right, so who cares about the stringent notion of explicitness? Actually, this thing is central to a number of important results. Okay? So the well-known result that if you take your favorite NP complete problems and you make a succinct version out of it, this becomes NEXP complete, relies exactly on clause-explicitness. And here the setting is that the running time is exponential in n. The length of the formula doesn't have to be quadrilinear, but can be poly-t, at least for this version. And you should be able to output the ith clause in time polynomial in the length of the index. Okay? And this notion is also important for lower bounds. Like, for example, the lower bounds for set that we have, like the ones in this paper and many others, rely on clause-explicit reductions. And the setting here is that the running time is poly n. The length of the formula critically has to be quasi-linear. Okay, this thing, the poly t size would not be enough for this. And the output of the clause should be doable in time a polynomial in the size of the index, and also space linear if you want the tightest results. Okay? And recently, the notion of clause-explicitness has been brought to the forefront by Williams' remarkable connection between lower bounds and satisfiability. Okay? So specifically with Williams' connection, if you want to prove a lower bound against a circuit class C, like for example ACC 0, then you benefit from having a clause-explicit reduction where the computation of the clause is done within the same class against which you're proving the lower bound. Okay? And here the setting is that the running time is exponential. The length of the formula critically, again, is quasi-linear. And again, the computation should be done within the same class against which you're proving the lower bound. Okay? Okay, so what was known about these reductions? Not much, actually. So there is a result which appears in a paper by Aurora, Stoyer, and Widerson, in which, for the simpler notion in which the length of the formula is polynomial in the computation, they get computation of the clauses in AC0. Okay, so what I mean by this, again, is that there is a circuit AC0 of size just polynomial in the index to a clause which can output the clauses. Okay? This maybe is also folklore, no, whatever, yeah. So.
Was first.
Folklore was, yeah, okay, good. So I think other people.
It's in the pattern.
Okay. Okay. Just you're never sure if you want, to give credit. Okay. So if you care about the tight bounds on the size of the formula, then in this PCP paper they give reduction also in which the computation is done in NC1. Okay. And that's pretty much all that was known. Okay, and in fact, more efficient reductions were considered by some to be hard or perhaps even impossible. Okay, so I mentioned earlier that Williams' technique can benefit from such reductions, and this means that in his proof he has to use a little workaround to get the lower bound, which also means that his connection was not as tight as one could have hoped for. Okay? And I will come back to this in a second. Okay, so what do? We prove that in fact you can have these clause-explicit reductions which are very efficient. Okay, so you can reduce computation that runs in time t to 3 SAT instances of the right size, quasi-linear, and each output bit of the reduction just depends on a constant number of bits of the index. Okay, so it has constant locality in the index. This is a class of functions which is also known as local, constant locality, NC0, or junta. Okay? Yeah.
What is the dependence on X?
So the dependence on X is also constant locality if your computation, if t is true to the n.
Is what?
If t is 2 to the n. So in the setting of exponential time, you get constant locality. If the running time is poly n, you must pay in X, and there's no way around it. Okay? But if it's if the running time is exponential, then you can encode X into the reduction map and preserve a constant locality. But that requires an argument. Okay? Yeah.
The running time of R1I should be like.
So you can probably make this linear time in some Turing machine model, but we did not go through it. Yeah. He asked what's the running time of R, and the answer is that you can probably make it linear time in a Turing machine model, say, but I didn't check that.
But that would be like order log the running time.
Or the linear time in the input. The input is I. No, the input is I, and you just output one clause. Input and output have the same length. Okay? So you could probably make this linear time in the input length.
Okay, so I'm confused there.
Okay, good.
Isn't it constant?
No, each output bit, so it's outputting many bits, so it cannot be constant. It's outputting. So to make this completely visual, here is how a possible clause in the output can look like. Okay, so you give me I, this is a possible clause. Each of these variables has a bunch of bits. How many bits? It's about length of I. Okay? And you also have 3 sign bits for this thing. So each of these bits, so each bit of the representation of each variable just depends on a constant number of bits of I. Okay? Yeah.
So the exponent in the log that is, I'm going to get, do you get it down to close to 1 or? Is it...
Probably not. Yeah, probably it's not very optimized. Yeah, though you probably can, but yeah, we didn't bother. But okay. Is the result clear? Okay. So this is pretty much is taking length of I bits in input, and the output is about 3 times length of I. About, okay. All right. So this model is fairly restricted. In particular, these maps R can't even add 1 in binary. Okay. So with constant locality, you can't even add 1 in binary. So, and I will come back to this to tell you where it's a problem. Okay. In fact, we get a number of other reductions which have incomparable features. Okay. And I just want to highlight one here. So in the previous slide, I mentioned constant locality. But what about getting the locality like 2 or maybe even 1? Okay? So we don't know. It may be impossible. But for the specific application of getting lower bound Sala-Williams, in fact, we give an R, which is a reduction which is as efficient as possible. So we get us locality 1. That means that the map is doing nothing, essentially, just rewiring the edges. And it's like the circuit that's computing the clause isn't there. Okay? So this gives a zero overhead application for the zero overhead cost for the application of lower bounds Sala-Williams, and gives some of the tightest results. And I'm going to mention them now.
That's equivalent to saying it's a projection, right?
Yeah, so it's a projection.
So there are no NOT gates? It's really
They're all, so as long as your circuit is, as long as you can negate things, you just negate and rewire. So as long as you can swallow the knots, okay? So the cost of computing the clauses is 0 in the reasonable model. And so I want to tell you what consequences these things have, and that's what I'm going to discuss now. So first, just some background on Williams connection. So, sorry, that comes afterwards. So first, just some simple consequences. So just to get to the same page, so I mentioned earlier that succinct 3-sat and succinct 3-coloring being NEXP complete relies on clause-explicitness reductions. So now we get that these problems remain NEXP complete even if they're encoded by NC0 circuits. Okay? And we also get a slightly strong resist 0 lower bound. Okay? So whatever Williams can do, we can shave off just the constants just a little bit. Okay? But the more interesting consequences are for a somewhat tighter connection between satisfiability and lower bounds following Williams. So first of all, a reminder that when I say lower bound, as in Williams, I'm going to mean a lower bound for a function in NEXP or even in e to the MP. Okay? And when I say Sala algorithm, I'm just going to mean something which runs faster than brute force by superpolynomial amount. Okay? So in Williams' paper, you can get a lower bound for circuit of size S and depth D if you have a Sala algorithm for size which is polynomially bigger, like S to the C, and depth C times D. Okay? And a high-level improvement is that with these constant locality reductions, we just need its algorithm for size c times s and depth d plus c. Okay? And this constant c now we really tighten the screws and we try to make them as small as possible. And I want to tell you about that. So first of all, we get a connection between algorithms and lower bounds for a number of new classes which have been studied in the past. Okay, so for all these things, so these are 4 classes, and for each of these, if you have a algorithm, now you get a new lower bound. So this includes linear side circuits, and 2 classes which are from Valiant's seminar paper, linear size log depth and linear size series parallel. Okay? And we also get, for quasi-polynomial cement, which would be a significant extension of Williams' result. Okay? Okay, so all these things could not be obtained before because of the loss in the connection. Okay? And something which is interesting is that these things can be related to assumptions about KSAT. Okay? And I'm going to tell you about this now. So the first such connection is actually in Williams' paper. So he shows remarkably that if the ETH is false, the exponential time hypothesis, then you have a linear size circuit lower bound. Okay? And in this paper, we also give an alternative proof of this, which is basically one line. So you just apply Cook-Levin to the previous result. Okay, so let me go back one slide. If you can prove a connection for linear side circuits, you can just reduce linear side circuits to a 3-sat instance. Okay, so it's just one line with this framework. But we can do more. So now we also get lower bounds if the strong ETH is false. Okay. This time, the lower bound is for linear size series parallel circuits. Okay. And we get other lower bounds under assumptions which still don't have a name. Okay. Okay, so, and I want to tell you one more thing, which is about making the constant as small as possible. Okay. So recall that 3n lower bounds is not known. So for general circuits under the full basis, we don't know how to prove that. So it's a very modest goal, perhaps, but let's see what we can do. So we can now show that you will have such lower bound if you can place 3-sat in time 1.07 to the n. Okay? And in fact, if you are happy with a lower bound for a function which outputs 2 bits, it's enough to get 3-sat in time 1.1 to the n. Okay, so the record is 3-sat in time 1.34, okay, by these people here, like building on previous works. There is still a gap, but still I want to emphasize these results because it seems to be the first time that this numerical value here has an application for complexity lower bounds.
So okay. if you had 1 plus epsilon to the n, what would that give?
It would be a much, I mean, if epsilon becomes very small, it becomes a much better result. It would be like, what's that? It becomes like 4n or 5n lower bound. I mean, I didn't do.
Right? If the ETH is false, if you get 1 plus epsilon for every epsilon, then you get
C and lower bound very constant.
Yeah. So yeah. Okay. So I want to make one last point about the consequences about whether these results simplify the proof that NEXP is not in NEXP 0. And to answer this question, let's recall that Williams uses as black box previous reductions. So if instead you take ours as a black box, the proof is simpler. Okay? In fact, that's how he presented at the bootcamp. Thank you. In fact, if you just want this, it's enough to get a reduction which runs in NEXP 0, which is much simpler. And I will tell you in a second how it's done. Okay. And this thing was done independently by Kovansky and Van Meckebik. Okay. Any questions about this? Otherwise, I'm going to move to the proofs. Okay. So I want to tell you how we prove this local reductions result, and along the way I want to tell you about some background material which I think is exciting and should be known more broadly. Right, good. Okay, so our goal is this. First I'm going to forget about 3-SAT, okay, and I'm going to think of circuit SAT. Okay? So I want to, so I have some computation which runs in time t, and I want to reduce it to a circuit SAT instance C, which has quasi-linear size, okay? And what I need to do is that I have a map R which has constant locality, and given an index I to a gate in this circuit, it should be able to output the type of that gate, if it's OR, AND, or constant, and the children of this gate with constant locality. Okay? So that's sufficient because the standard reduction from circuit SAT to 3-SAT preserves constant locality. Okay? So how do you do this? So the standard way, perhaps, to get such small circuits is to use the Pippinger and Fisher oblivious simulation. However, it's not clear how you get this constant locality result from that. Okay? It may be possible, but even if it is, it seems quite complicated. Okay? However, Gurevich and Shila introduce an alternative way of simulating computation, which I'm going to call the sort and check technique, which seems useful. However, in their paper, if you want to use it, you still go back to the Pippinger and Fisher oblivious simulation. So instead, we use a variant by Van Merkevik, okay, which is pretty cool, which is just like Gurevich and Shila, but at the critical point, which I'm going to mention in a second, it uses sorting networks. And by doing so, he avoids the Pippinger and Fisher simulation. Okay? So this variant, which I'll describe in a second, seems to be strangely unknown, or little known. It was actually rediscovered by students of mine in a class that I was teaching. We actually spent months doing it. Then we put it online, and after 1 hour, we got an email from Van Merkevik saying, with a pointer to the section in his survey where it does the same thing. So the students lost confidence, but I pushed them to continue working, and we got this result, which was then rejected, but that's okay. Okay, so how does it work? So here's how the circuit looks like. And I wrote it on the board, but because of a technical problem, I couldn't finish the drawing. So there's a bunch. So the input to the circuit are a bunch of configurations. I'm just going to write the sizes here. These are size order of log D. So there are these checks circuits which have size poly log T. And there's a sort part which has size T times poly log T. Okay? So with this picture in mind, I can now describe what this simulation does. So the input to the circuit SAT instance C is a series of T configurations, where each configuration just takes order of log T bits and encodes the state, the timestamp of the machine, and it has pointers and contents of a constant number of memory cells. So you don't encode the entire memory, just a constant number of bits. Okay? That's the input. And what the circuit does, first, it does a bunch of pairwise checks. Specifically, it checks if every computation follows from the previous one, assuming that what you read in the memory is correct. Okay, so you're just going to check timestamp and state changes. Okay, then you're going to sort all the configurations by memory locations which they address. Okay, so you're going to put first all those which address the memory location 0, then all those which address the memory location 1, and so on. And once you have that, it's easy. You can still do some pairwise checks to check the consistency of the memory locations. So if you ever read a 0 in a memory location, you check that the previous time a 0 was written there. Okay.
If a configuration uses C memory blocks, you make C copies of it, or?
Configuration, you may have C pointers to memory bits. So you have C pointers. That will be C times log T.
So you sort each pointer.
So okay, yeah. So good. So if you have more, you can sort it like T times. Yeah. You can sort it by the first pointer and then the second pointer and so on. Yeah. Thank you.
So each little configuration is just like what was changed about.
So each configuration, it's a snapshot of what the machine is looking at the moment. So it's like the timestamp, the state, and just the constant number of bits with the machine is looking at, but not the entire memory. Unlike the textbook configurations.
It's like a single tape machine.
So thank you. So the good thing about this is that I'm gonna forget about Turing machines. So. You can think actually of a RAM model, and you will have the same thing. So the machine can address any bit of memory by following a pointer.
So when you say sorted, then if there's more than one pointer, what do you mean?
Yeah, so that's what the boss was asking. So thank you. So if you have more pointers, you can sort by the first pointer and then the second point. So this thing will blow up T times.
C prime and C double prime and C triple prime. Let's say there are 3 pointers.
Yeah. So yeah, that's what. But probably 2 pointers are universal probably. But
I think this pointer may be like a red herring. So you're just saying, look at a transcript of the computation. You're saying, oh, at time t, I read a 0 from position I.
That's a pointer, right? So
you can call it a pointer or not, but and then at time t plus 1, I wrote to position 1 to position j. So you have a list of things that could have happened during the computation, and then you sort that list of read and write operations first by memory address, the memory cell address, so that they're all lined up, and secondly by time, so that they're all in chronological order, and then you check that every read was reading the bit that was written there last, and every write was,
Right.
Yeah.
Saying with almost generality, you can assume one thing is read, one thing is written.
That's right.
yeah.
So you don't have to sort them.
Yeah. Okay.
Let's break it into like one reading.
Yeah. So if you don't want to sort T times, you can probably assume to just read and write one thing at a time. But yeah. So I think this thing, if I read a book on complexity theory, I'll probably put this thing in chapter 1. I don't know. I think it's pretty cool. And also there's been some talking about connections between algorithm and complexity. So I want to, make an obvious observation that sorting matters to complexity theory. Okay, so the fundamental algorithm is important for a fundamental reduction in complexity theory. All right. So let me go back to our task, which is making this thing constant locality. Okay, so remember that what I need to do is that I get an index somewhere here, and I must be able to output the children of the gate with constant locality. So each output bit of the description of the children should just depend on a constant number of bits of the index I. And if you look at the picture, there are basically 3 things that you have to deal with. Okay, so the first one are the check that you perform. Okay, so maybe I get an index here. This check or this check here must be able to index the children of this circuit here. The second thing that stands out is the sorting, right? So this thing is huge. As I said, t times log t. I may get an index here. I have to index this. And the third thing is a little bit more subtle to see is the +1. Okay, so I'm using +1 here And it takes a little bit of time to see again, but I may get an index here. I must be able to access both, the ith configuration and the I+1. So somewhere I'm computing this I+1. Okay. So the first thing that I want to convince you of is that if you just care about AC0 reduction, this stuff is fairly simple. Okay. So why is that? And we're also going to see the various sizes of things. So if you just want R in AC0, so the checks are trivial because this stuff is small. Each check, it's a polynomial computation in the size of the configuration, so just a polylog t gates, okay? And, the index that, you can perform, you can complete the index at this subcircuit in brute force with a DNF even. Okay, so without even thinking what this thing is doing. Okay, so the checks are small because they just index 2 configurations. The sort is huge, okay, it's about 3 configurations. This thing is not trivial, but it's an exercise to see that if you use like odd even merge sort networks, you can actually compute the children with AC0. Okay? And this +1 business is also trivial because AC0 can add. Okay, so if you give me this index here, I can add 1 in via a DNF, and I get this configuration here. Okay, so that's all that you need if you want to place this thing in AC0. But we want it in NC0. Okay, so constant locality. So that's harder, and for that, each of these things will require some technique. Okay. And I want to spend one slide about each of them, if I have time. So first, let me tell you about how you get these checks. Okay. Okay. So these checks are small, but if I just have constant locality, they're still big, right? Because anything is big compared to a constant. So what we do here, we actually use, again, a general technique that allows us to not even care how this thing is actually done, which is always good if you can do it. So the first observation is that these checks, like pretty much any algorithm that does anything that's, that arises in practice, are log space uniform. Okay, so these are, decent circuits which are log space uniform. Okay, so log space is in the size of this small circuit here. Okay, you can index the connections on this thing by log space machine. Okay, this is true, like for multiplication, for addition, for like all the standard algorithms, and even for this one. And then we prove a general result, which we call a spreading computation, that if you just care about the uniformity, and if you allow for a poly-size change in the size, log space uniformity is the same thing as constant locality uniformity. Okay, always. Okay, so you just hit that with this, and the check circuit are done. Okay, so we cannot apply this thing to the whole circuit because you blow up the size by a polynomial, which we cannot afford. But here, if you make this thing a little bit larger, it's okay. And then again, you get the constant locality. How is this thing done? So the technique goes back to Ruzzo, and it's about adding gates to the circuit which encode configurations of the log space machine. Okay. However, Ruzzo does not aim or prove constant locality, and with constant locality it's a little bit trickier because you can't even check if a configuration is valid or not. So actually the new circuit here will have a bunch of stuff over which you have little control, but it will still correspond to a correct computation. Okay? Okay, so again, you add gates which correspond to the configurations of the log space uniform machine, which index this. And then the connection within those can be done with constant locality. The second thing that we need to deal with is the sorting, and here actually we tried very hard to get a sorting network that we could index with constant locality, and we couldn't. So the best that we could do is log depth decision tree, and we wrote it up actually in a different paper because we thought it was of some interest to have this. So to get constant locality, we actually go instead to routing networks. Okay? So routing networks are a different object in which you can implement any permutation that you want, including the one given by sorting, but you have to use some additional non-deterministic bits here. And this actually was done in the PCP literature since Polishuk and Spielman, but not so much in the more classical literature. And if you use de Bruijn graphs, you can actually index, you can compute the children of an index I just by rotating I and XORing by constant, which is exactly what we want to do. Okay? And the last thing is this +1. So I still need, if you give me index here to index the next configuration. And this cannot be done with constant locality, which are various things. And one thing that works is this, is actually to twist the whole thing. So I'm going to use the routing network in a different way. So instead of using this circuit here to compute the permutation given by the sorting order, I'm going to use it to implement the successor with respect to the order given by the sorting. Okay?
Ask for the carry bits to be given to you as an additional auxiliary variables?
We tried, but it seems like you need to double the size of the index if you do that, which you cannot do, because if you double it means squaring the whole circuit. So that's one thing that we thought about. This thing is a little. So the issue is that here, you sort of you go in a line, so all these things are connected by doing this +1. With this new system, the checks can be aligned with configuration. So you always have the same shift that you have to apply to the index to get to the next configuration. Okay? So instead of sorting, you compute a successor function. Okay, and that's so these are the three main ideas that go into this, and I just want to tell you if I have time. Actually, I don't remember what time I started. Okay, well, I got to continue. So I want to tell you just 2 slides about PCP reductions. And is it over? Okay. So just 5 minutes, 20 minutes. Okay. So whatever I said about classical reductions also applies. I mean, the same motivation that you have for classical reduction also applies to PCP reductions. Okay, perhaps even more so. So in particular, Williams' paper gives overbounds from randomization, which should be easier to obtain. And the same issues are there. So the more efficient the PCP reduction that you get, the tighter the connection. And because very efficient reductions were not known in his paper and later with Santanam, he has a workaround. So what we do here, is some step towards making them efficient, but it's still wide open. So there is this paper by Ben-Sasson, Goldrake, Harsh, Sudan, and Badan, which I mentioned earlier. They give a PCP which applies to any running time, including through the end, where the number of constraints is quasi-linear, which is what you want, and the number of queries is polylog, which is not what you want, but it's something. And the computation of the query from the index is NC1. Okay? So Mie has later improved in a beautiful result this polylog to constant. Okay? But we are not able yet to exploit this. So we just look at the original construction. So we get a variant of this in which the computation of the queries from the index, again, has 0 cost. So it's just locality 1. So it's just a projection. And this thing is easier to do than before because here I'm allowing many queries. So getting this with just a constant number of queries seems to be an important step. And then the post-process is a CNF. Okay? So this thing tightens some of the connections, but I don't want to spend too much time on that. Instead, I'm just going to conclude and say that we have seen that you can reduce non-deterministic time to 3 SAT instances which have size quasi-linear in T, and the ith clause can be computed with constant locality from the index. Okay? And the previous best was NC1. And it's now easier to get null over bounds from set algorithm. So you quote-unquote just need to prove that the strong ETH is false, or that 3 SAT is in time 1.1 to the n. Okay? And we also get similar but weaker results for PCP reductions. So one thing which I think is interesting is to understand if, with respect to clause-explicitness, PCP reductions are inherently more difficult than classical reductions, okay, which we don't know. Thank you. Yeah.
Can you give a new proof of a non-trivial but known lower bound for circuit classes? Like, you need something like that to establish 3 to the n lower bound. But can you establish a known like 2 times n lower bound?
You probably can. Yeah, you can prove probably one plus epsilon and lower bound. I mean. Yes, so just plug in the known 3 SAT. Yeah, I think so. Yeah.
Depends on what the constants are, right? So,
yeah. No, I think. Well.
So what circuit lower bound can you establish just taking Suguru's recent 1.34?
So there is a little loss that needs to be overcome because you're taking multiple copies of the circuit. But I believe, though I haven't checked, that if you start with a circuit of size n. Then you get something, like you get overbound for those circuits. But I haven't. I mean, as long as so you're making 2 copies of the circuit, and you need a 3 SAT algorithm to be faster than that loss. But I think it will be. But I haven't checked. But in any case, it wouldn't be that, right? I mean, you get like
a strange proof for a known result.
Yeah, strange proof. Yeah. So I think it probably yes. The answer is yes.
The technical question. So when you say local constant locality, so you have this rewiring, how much do you need to compute this rewiring? Like how uniform is this sense of your circuit?
So I think it's very uniform, and I think you can probably get R, which is simultaneously constant locality and the linear time on a one-tape theory machine. But I have not checked that because there is really nothing going on. I mean, the spreading computation, what we call, the connections here will just need to take one step of the log space uniform describer. So that's like linear time. Definitely, here it's like super simple. You just rotate again XOR. So I think it probably would be linear time in a strictest possible model computation, like one tape. But I have not checked that because for this application to lower bounds of circuits, you don't need that. Like maybe later for 3 SAT for like SAT lower bounds, you will need the uniformity. I think it just I think it's a somewhat cleaner model. Just have the locality bound as opposed to like are you using one tape Turing machine or a 2 tape Turing machine? But
Any other questions? Thank you.